There is a moment each day when the sun disappears, yet light remains. Not the harsh brilliance of noon, nor the absolute darkness of midnight, but something between a transition so gradual, so exquisitely timed, that ancient civilizations built monuments to mark its passing. This is twilight, and for 3,000 years before the first telescope magnified the heavens, Egyptian astronomers were measuring it with remarkable precision. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed because tomorrow I've saved something extraordinary for you. Picture the great temple complexes along the Nile, where stone markers cast shadows across carved surfaces. These weren't mere decorations. They were instruments, shadow clocks that captured something most of us have never stopped to consider. Twilight's duration changes as you move across Earth's face. In Memphis, twilight lingered for 12 minutes. Travel north, and those minutes stretched longer. The pattern was undeniable. The world, these ancient observers realized, was revealing something fundamental about its very shape. What they were witnessing, though they couldn't know the complete mechanism, was light performing an extraordinary feat. When our star drops below the horizon, it doesn't simply vanish. Its light continues painting the sky, bending around Earth's curve through an atmosphere that extends 99 kilometers above our heads. Think about that for a moment. 99 kilometers of air, pressing down with the weight of an ocean, creating a lens that curves starlight itself. The photons arriving in tonight's twilight left the sun 8 minutes ago. They've traveled 150 million kilometers through the vacuum of space at the speed of light. 299,792,458 meters per second, if you want to be precise. And then, in the final moments of their journey, something remarkable happens. They encounter our atmosphere. When the sun sits exactly 6 degrees below the horizon, civil twilight begins. This isn't an arbitrary number, it's the precise angle at which light bends through atmospheric layers to create 500 lux of illumination at the surface. 500 lux. That's bright enough to read newspaper print comfortably, bright enough to distinguish colors, to see faces clearly, to navigate without artificial light. Our ancestors knew this threshold intimately. They planned their lives around it. But twilight doesn't remain constant. As Earth continues its rotation, the sun sinks deeper. At 12 degrees below the horizon, nautical twilight arrives, named not by astronomers, but by sailors who lived or died by their ability to measure angles in fading light. At this depth, illumination drops to 5.4 lux. This is a threshold of tremendous importance, though you might never have noticed it. It's the exact brightness where human color vision begins to fail. Your eyes contain two types of photoreceptors. Cones, which distinguish colors, require reasonably bright light to function. Rods, which detect only shades of gray, work in much dimmer conditions. At 5.4 lux, you cross from one world into another. Colors drain away. The landscape transforms to silver and shadow. Objects that were clearly red or green or blue just minutes ago become merely light and dark. The world becomes a charcoal sketch. Continue watching, and the sun descends further still. At 18 degrees below the horizon, astronomical twilight reaches its end. Illumination has fallen to 0.008 lux darker than a quarter moon night. This is the threshold beyond which the faintest stars become visible, where astronomers can finally begin their observations of the deep universe without interference from scattered sunlight. These three kingdoms of twilight civil, nautical, astronomical, aren't human inventions. They're natural divisions written into the physics of how light interacts with matter. Ancient observers couldn't explain why these boundaries existed, but they could measure them, and one of them used those measurements to accomplish something extraordinary. In 1000 CE, A Persian mathematician named al-Biruni stood on a mountaintop. He had travelled there specifically to observe twilight, bringing instruments he'd designed himself. Night after night, he measured the precise moment when twilight began and ended. He tracked the angles with obsessive care, and then he performed calculations that would have seemed impossible to his contemporaries. Using only twilight observations, no satellites, no modern instruments, nothing but careful measurement and brilliant mathematics, al-Biruni calculated Earth's radius. His answer: within 15 kilometers of the actual value. 15 kilometers out of Earth's 6,371 kilometer radius. An error of less than 1/4%, achieved by watching light bend through air. Consider what this means. A man standing on a mountain, watching the sky change color, unraveled the size of his world. He understood that light traveling through atmosphere doesn't travel in straight lines. It bends, it curves. It follows paths determined by the density and composition of the air it passes through. And if you're clever enough, patient enough, careful enough in your observations, those bending rays reveal the dimensions of the planet itself. This is the power of twilight. Not simply beauty, though it is beautiful, but information. Every gradient of fading light, every shifting color, every minute that twilight lasts or fails to last tells us something about our world. The thickness of our atmosphere, the curvature of our planet, the composition of the air we breathe. When you watch the sun set tonight, you're witnessing the same, the phenomenon that captivated those Egyptian observers 3 millennia ago. The same physics that allowed al-Biruni to measure a world without leaving a mountaintop. The same interplay of light and matter that continues, without interruption, every single day on every point of Earth's surface where the sun can be seen. But here's what makes it truly extraordinary. Twilight isn't just passive illumination. It's an event that triggers responses across the entire web of life. Plants that spent eons evolving on this planet have learned to read twilight signals with extraordinary precision. Animals time their most critical activities to its arrival. Even our own bodies respond to twilight in ways we're only beginning to understand fully. That Egyptian astronomer, marking shadows on stone, was measuring more than light. He was measuring the pulse of a living planet. The moment when day-active creatures retire and night-active creatures emerge. The transition that governs when flowers open, when bees return home, when predators begin their hunt, and prey animals seek shelter. Twilight is, in essence, the planet taking a breath between two states of being. Not day, not night, something between. A liminal space that exists nowhere else in exactly this way. Earth's atmosphere, you see, is unusual. Mars has air too thin to create meaningful twilight. Venus has clouds so thick that its surface experiences only murky gloom. Mercury has no air at all. The sun simply blinks out the instant it drops below the horizon, like a light switch being thrown. But Earth, with its nitrogen-oxygen atmosphere at just the right pressure, with water vapor and particles suspended at just the right concentrations, creates this daily masterpiece. The light you see during twilight has traveled an extraordinary path. Those photons don't just pass through atmosphere, they collide with it. They strike molecules of nitrogen and oxygen, molecules so small that 8 million of them side by side would barely span a millimeter. Each collision scatters light in a new direction. Blue light, with its shorter wavelength, scatters more readily than red, which is why the sky is blue during the day, and why twilight progresses through that glorious sequence of colors, gold to orange to red to purple, as the sun descends and light must travel through ever more atmosphere to reach your eyes. At noon, sunlight passes through 1 atmosphere's worth of air, call it 1 unit of atmosphere. At sunset, when the sun sits right on the horizon, light must travel through 38 atmospheres. During civil twilight, when the sun is 6 degrees down, Light passes through 50 atmospheres or more. The path becomes longer, the scattering more intense, the colors more dramatic. This is why twilight isn't simply dim daylight. It's fundamentally different light, filtered and scattered and bent by its journey through increasingly oblique angles of air. Every photon that reaches your eye during twilight has bounced off countless air molecules, each collision altering its path slightly until the accumulated effect curves light around the very edge of the planet. Think about what this reveals about observation itself. Those ancient astronomers possessed no special instruments beyond carefully placed stones and patient eyes. Yet they discovered patterns that revealed the shape of Earth, the structure of the atmosphere, or the behavior of light itself. They transformed simple observation into profound understanding. This is what twilight offers us still. Not just beauty, though. Stand beneath a twilight sky and try to deny its magnificence, but insight into physics, into biology, into the fundamental ways our planet functions as a system. Every sunset is an experiment in atmospheric optics, performed free of charge, requiring only that we pay attention. And tomorrow we'll explore what happens inside that twilight, the extraordinary divisions of light that mariners navigated by, that photographers chase, that mark boundaries in the natural world as precisely as any fence or wall. 3 kingdoms of fading light, each with its own character, each triggering different responses from the living world. But for now, simply remember this. When the sun disappears tonight and light remains, you're witnessing something ancient and ongoing, a phenomenon that hasn't stopped for 4.5 billion years. Light bending around the world, painting the sky in colors that exist nowhere else in our solar system, marking the daily transition that every living thing on this planet has learned to recognize. Twilight isn't merely the absence of day or the prelude to night. It's a state unto itself, as essential to Earth's rhythm as tides or seasons, as measurable as any other natural phenomenon, and as worthy of wonder as anything the universe has to offer. The photons illuminating tonight's twilight began their journey from the sun's core 100,000 years ago, bouncing between atoms in that dense stellar furnace until finally reaching the surface, then racing across space to paint our sky for these brief minutes before darkness claims them. And tomorrow night, the eternal dance begins anew. Civil twilight arrives first, like the opening movement of a symphony. In most inhabited places, it lasts 20 to 30 minutes, though this is one of those measurements that varies wildly depending on where you stand on Earth's surface, something we'll explore more deeply soon. For now, picture this threshold moment when the sun has just dropped below the horizon but the world remains bright. Street lights stay off. You can still read a book outdoors. Faces remain clearly visible. Colors haven't yet begun their retreat into grayscale. This is the time photographers call the golden hour, though that name is something of a misnomer. It's not an hour at all, and the light isn't particularly golden yet, but it is transformative. Here's why. At noon, when the sun blazes directly overhead, its light passes through the shortest possible path through our atmosphere. The journey is swift, the scattering minimal, the light harsh and direct. But as the sun descends toward the horizon, that path lengthens. By the time civil twilight arrives, sunlight must travel through 40 times more atmosphere than at noon. 40 times. Let that sink in for a moment. Every photon reaching your eye has navigated through 40 times as much air, colliding with 40 times as many molecules, scattering and rescattering until only the most resilient wavelengths survive the journey. The result is light fundamentally transformed, softer, warmer, directional in ways that midday sun never achieves. Our atmosphere, you see, is primarily composed of 2 gases, 78% nitrogen and 21% oxygen. The remaining 1% includes argon, carbon dioxide, water vapor, and traces of other elements. But it's those dominant two, nitrogen and oxygen, that perform the magic of twilight scattering. Each molecule vibrates, not slowly, not in any way you could observe directly, but at extraordinary speeds. 10 million times per second, these molecules oscillate, and when light strikes them, they act as tiny antennas, absorbing and re-radiating that light in new directions. But, and this is crucial, they don't scatter all wavelengths equally. Blue light, with its wavelength of 450 nanometers, scatters 16 times more readily than red light at 700 nanometers. 16 times. This isn't a small difference. It's the difference between a sky painted blue and a sunset glowing red. During the day, blue light scatters so efficiently that it fills the entire sky, arriving at your eyes from every direction. That's why the sky is blue. But during twilight, sunlight must travel through so much atmosphere that most blue light scatters away completely before reaching you. What remains? The longer wavelengths, orange, red, and as twilight deepens, eventually purple, a mix of the longest visible wavelengths that can still complete that oblique journey through air. Watch carefully, and you'll see the progression. The sky near the horizon glows orange-red, where the sun descended. Higher up, where light travels through less atmosphere to reach you, yellows and golds dominate. Higher still, blues persist. And at the very top of the sky, in the opposite direction from sunset, you might glimpse the deep blue of approaching night. The entire dome of the sky becomes a gradient, a spectrum stretched across the heavens, each band representing a different path length through atmosphere. This is what those ancient photographers were chasing with their golden hour. Not just pleasant light, but light that reveals form and texture in ways impossible at any other time. Shadows grow long and soft. Contrast decreases. The harsh edges that characterize noon sunshine dissolve into something gentler. The world doesn't just look different. During civil twilight, it is different, illuminated by photons that have survived an extraordinary gauntlet. Then, as Earth continues its rotation, civil twilight gives way to nautical twilight. The name is no accident. This phase is named for the sailors who once navigated by the stars, using instruments called sextants to measure angles between celestial objects and the horizon. But here's the challenge they faced. To use a sextant, you need to see both the stars and the horizon line simultaneously. Too bright, and stars vanish in the overwhelming scatter of sunlight. Too dark, and the horizon disappears into blackness. But there's a window, a precise window when both remain visible. That window is nautical twilight, when light levels drop from 5.4 lux to 0.54 lux. 5.4 lux. Remember that number, because it marks one of the most significant transitions in human perception. This is the exact brightness, where your color vision begins to fail, where your eyes switch from relying primarily on cone cells, which detect color but require relatively bright light, to rod cells, which function in dim conditions but see only in shades of grey. You've experienced this transition countless times without necessarily recognizing it consciously. That moment when colors seem to drain from the landscape, when the green leaves become merely light or dark, when the red car and the blue car become indistinguishable, that's 5.4 lux. That's nautical twilight's arrival. But something else happens at this threshold. While you lose color, you gain sensitivity to contrast and motion. Rod cells, those dim light specialists, are extraordinarily good at detecting movement. This isn't coincidence, it's evolution. For millions of years, our ancestors faced their greatest dangers during twilight. Predators that hunt at dusk evolved to use this transitional light, and so did prey, developing enhanced motion detection precisely when they needed it most. So when you feel that slight unease during twilight, that sense of heightened awareness, you're not imagining it. Your visual system is genuinely switching modes, activating capabilities that remain dormant during bright daylight. You're using the same adaptations that kept your ancestors alive when saber-toothed cats prowled the dusk. Ancient mariners, of course, weren't thinking about predators. They were thinking about survival of a different sort, finding their position on a featureless ocean using nothing but angles and stars. During nautical twilight, they could measure the angle between Polaris and the horizon, or between the moon and a star, and from those angles calculate latitude with remarkable precision. The horizon provided their reference line, the stars provided their markers, and nautical twilight provided the exact light conditions where both could be seen. Consider the precision required. 2. Early in twilight, and bright sky overwhelms faint stars. Too late, and darkness swallows the horizon. The window of usability might last only 15 to 20 minutes. Yet for centuries, before GPS and radio and electronic navigation, sailors crossed entire oceans using measurements taken during this brief window. Their lives depended on recognizing the exact moment when nautical twilight reached its optimal point. Then comes the final phase, astronomical twilight. The sun has now sunk between 12 and 18 degrees below the horizon. Illumination drops below 0.54 lux, entering ranges where even adapted human eyes struggle to see clearly. This is the realm of faint stars and subtle phenomena, invisible during brighter conditions. At 18 degrees down, when astronomical twilight ends and true night arrives, illumination reaches 0.008 lux. To give you a sense of scale, that's darker than a quarter-moon night. It's dark enough that the Milky Way becomes visible if you're far from city lights. Dark enough that planets cast subtle shadows. Dark enough that astronomers can finally observe the universe without interference from scattered sunlight. But astronomical twilight itself, that transition from nautical twilight to true darkness, hosts its own wonders. One of the most remarkable is the zodiacal light, a phenomenon so subtle that many people have never seen it despite living their entire lives under the same sky that displays it. The zodiacal light appears as a triangular glow rising from the horizon in the direction where the sun has set. It's not atmospheric in origin. Rather, it's sunlight reflecting off cosmic dust, tiny particles orbiting the sun in the same plane as the planets. These dust grains, remnants of comets and collisions between asteroids, form a disk that extends throughout the inner solar system. During deep twilight, when the brightest stars are visible but the sky hasn't yet turned fully black, this dust reveals itself as a ghostly pyramid of light. To see it requires darkness, true darkness, not the light-polluted skies above cities. It requires astronomical twilight, specifically that window when the sky is dark enough for the zodiacal light to stand out, but not so dark that you lose sight of its subtle glow against the background of space. And it requires knowledge, because if you don't know to look for it, you'll almost certainly miss it, dismissing it as a stray cloud or the last remnants of sunset. But when you do see it, when you stand beneath a dark sky during astronomical twilight and recognize that triangular glow for what it truly is, you're witnessing something extraordinary. You're seeing matter that exists between worlds, dust orbiting through space, millions of kilometers away, revealed only because of the precise angle of sunlight during this specific phase of twilight. This is what the three kingdoms of twilight offer, not just gradations of darkness, but windows onto different aspects of our world and the space beyond it. Civil twilight reveals atmosphere and scattering. Nautical twilight marks the transition in human vision. Astronomical twilight unveils phenomena too subtle for brighter conditions. Each phase lasts a different duration depending on latitude and season, something we'll explore in depth later. But the sequence never changes. Civil, nautical, astronomical. Light fading through precise thresholds, each one governed by the angle of the sun below the horizon, each one creating conditions that trigger specific responses from both living things and human observers. These aren't arbitrary divisions invented by astronomers looking to categorize the world. They're natural boundaries discovered through observation. Sailors found nautical twilight because their instruments required it. Astronomers defined astronomical twilight because their observations demanded it. Civil twilight acquired its name because it's the threshold of human activity without artificial light, the moment when civilization transitions from day to night, operations. The boundaries are written into physics. 6 degrees, 12 degrees, 18 degrees. These aren't round numbers chosen for convenience. They're the angles at which atmospheric scattering creates light levels that correspond to genuine transitions in visibility, in color perception, in the ability to see both ground and sky simultaneously. And here's what makes it perpetually fascinating. These three kingdoms paint themselves across Earth's sky every single day. Twice a day, in fact, once at sunset, once at sunrise. The same physics, the same progression, the same thresholds, but never quite the same appearance because atmospheric conditions vary. Dust content changes, water vapor rises and falls. Clouds scatter light in unpredictable ways. Temperature inversions bend light paths. So while the structure remains constant, civil, nautical, astronomical, the actual appearance is infinitely variable. No two twilights are precisely identical. Each one is a unique performance of light and matter, played out across the stage of the sky, following the same fundamental script but improvising the details. Tomorrow, we'll explore the spectacular phenomena that occur within these kingdoms. The green flash that lasts barely more than a second, the belt of Venus that wraps our entire planet, the crepuscular rays that stretch across half the sky. These are Twilight's greatest performances, the moments when atmospheric optics create displays that rival anything else nature has to offer. But understanding them requires first understanding these kingdoms, these fundamental divisions, because the green flash occurs at a specific moment during civil twilight. The belt of Venus appears during the transition to nautical twilight. Noctilucent clouds, which we'll discuss in detail, are visible only during deep twilight when the sun illuminates clouds that float at the very edge of space while the ground lies in darkness. The three kingdoms aren't just a classification system. They're a map of when and where Twilight's wonders appear. Master these boundaries, understand what they represent, and you unlock the ability to predict and observe phenomena that most people never see, despite looking at the same sky. Light bends, molecules scatter, the sun descends, and the sky transforms through three distinct phases, each one revealing different truths about our atmosphere, our vision, and the space beyond our world. There is a flash of green light, pure and emerald, that appears at the moment of sunset. It lasts exactly 1.7 seconds. Most people have never seen it. Many don't believe it exists, dismissing reports as optical illusion or wishful thinking. But it's real. Photographer after photographer has captured it. Scientists have measured it. And in 1869, Jules Verne saw it from the deck of a steamship and was so captivated that he wrote an entire novel about it. The green flash, le rayon vert, as Verne called it, is a natural prism created by atmospheric layers. Here's what happens. As the sun touches the horizon, its light must pass through ever-thickening layers of atmosphere. Different layers have different temperatures and densities. Each layer bends light slightly differently, like looking through a stack of different glass lenses. This layering splits sunlight into its component wavelengths, separating colors just as a prism would. Red light bends least. It appears to set first. Orange follows. Then yellow, green, blue, violet. But here's the trick. Violet and blue scatter so readily in the atmosphere that they disappear almost instantly. What remains, for just over a second as the sun's final edge drops below the horizon is pure green. 1.7 seconds. That's the average duration, though it varies slightly depending on atmospheric conditions and the speed at which the sun appears to set. At the equator, where the sun drops quickly and perpendicular to the horizon, the flash is brief and intense. At higher latitudes during summer, when the sun sets at a shallow angle, the flash can last fractionally longer. To see it requires clear air at the horizon, no clouds, no haze, no pollution. This is why sailors see it more often than landlubbers. Over open ocean, the horizon is genuinely clear, unobstructed by mountains or trees or buildings. The air is often cleaner than over land, and crucially, on a ship, you're elevated above the surface, which provides a longer view through the atmospheric layers that create the effect. But the green flash isn't Twilight's only spectacular performance. Look opposite the sunset, toward the east, and you'll see something equally remarkable: the belt of Venus. It appears as a pink band wrapping around the entire horizon, sitting exactly 10 to 20 degrees above where you're standing. Below it, Earth's own shadow rises as a blue-grey arc. Above it, the sky darkens toward night, but the belt itself glows soft pink, like a ribbon stretched across the world. What you're seeing is backscattered light, sunlight that has already passed through the atmosphere, travelled over the curve of the Earth, and scattered back toward you from the eastern sky. The pink colour comes specifically from red wavelengths, the longest visible light that survived the double journey through atmosphere. Shorter wavelengths scatter away, only red persists, and backscattered red appears pink against the darkening sky. The shadow below is Earth itself, your planet's silhouette, cast onto its own atmosphere by the setting sun. As twilight progresses, this shadow rises, climbing higher into the sky as the sun sinks deeper below the western horizon. Eventually, the shadow engulfs the entire sky, and night has truly arrived. But during that transition, during those precious minutes when the belt of Venus is visible, you're witnessing a planetary-scale phenomenon. That pink band circles the entire Earth. Someone standing 1,000 kilometers away sees the same belt. Someone on the opposite side of your longitude sees it at their sunset, hours earlier or later than yours. At any given moment during twilight somewhere on Earth, the belt of Venus is painting itself across someone's eastern horizon. And then there are the rays. Crepuscular rays, from the Latin word for twilight, appear as golden or orange spears of light radiating from the sun's position. They shoot from behind clouds, spread across the sky like a fan, and can extend 500 kilometers from their apparent source. Here's what makes them extraordinary. They're actually parallel, perfectly parallel, like railroad tracks stretching toward the horizon. But perspective makes them appear to converge. Just as railroad tracks seem to meet at a distant point despite being the same distance apart throughout their length, crepuscular rays appear to radiate from a single point despite being parallel beams of sunlight. They form when clouds or mountains or buildings block some portions of the sun's light while allowing other portions through. The blocked areas create shadows that extend through the atmosphere. The unblocked areas create illuminated corridors, and because the atmosphere contains particles, water droplets, dust, pollen, pollution, the light becomes visible, like car headlight beams in fog. During twilight, when the sun is low and light must travel through maximum atmosphere, these rays become particularly dramatic. They can stretch across half the sky. They can appear both in the direction of the setting sun and in the opposite direction, anti-solar rays, or anti-crepuscular rays, where they seem to converge again at the anti-solar point directly opposite the sun. Think about what this means for a moment. Light from the sun, partially blocked by a cloud over the western horizon, creates shadows that extend across the entire dome of the sky, becoming visible as dark bands between bright rays, until they converge at a point directly opposite where the sun set. You're seeing shadows cast across hundreds of kilometers of atmosphere, made visible only because air isn't perfectly transparent, only because it contains enough particles to scatter light and reveal the geometry of where light travels and where it doesn't. But even these spectacular displays pale beside what happens when volcanoes erupt. When Mount Krakatoa exploded in 1883, it injected sulfur dioxide 20 kilometers into the stratosphere. At that altitude, far above weather systems, the particles persist for years, and they transform twilight completely. For 3 years after Krakatoa, twilights around the entire planet glowed blood red. The colors were so intense that fire departments in New York and Connecticut responded to what they thought were distant fires, only to discover they were looking at the sky. The light was bright enough to read by at midnight in London. Newspapers published daily reports on the remarkable sunsets. Artists painted them. Poets wrote about them. The entire world watched as volcanic aerosols created twilight displays unprecedented in recorded history. The mechanism is straightforward. Sulfur dioxide particles scatter light differently than normal atmospheric molecules. They're larger, for one thing, which changes the scattering pattern, and they're distributed at a different altitude, which changes which wavelengths get scattered away and which survive to reach ground level. The result was twilight dominated by deep reds and oranges, lasting longer and appearing more intense than normal twilight ever does. Scientists today study volcanic effects on twilight carefully because they reveal both how our atmosphere works and how volcanic eruptions impact global climate. Those same particles that created spectacular sunsets also reflected sunlight back into Indiverne, space, cooling Earth's surface by about 0.5 degrees Celsius for several years. The beauty came with consequences. But there's one twilight phenomenon rarer than green flashes, more subtle than the belt of Venus, more fleeting than even volcanic sunsets. They're called noctilucent clouds, and they float at the very edge of space, 80 kilometers high. To put that in perspective, most clouds, the cumulus and stratus and cirrus you see every day, float below 10 kilometers. Commercial airliners cruise at 11 kilometers. Even the highest thunderstorm anvils rarely exceed 20 kilometers. But noctilucent clouds exist in the mesosphere, at altitudes where the atmosphere is so thin that air pressure barely has meaning. They're composed of ice crystals exactly 100 nanometers wide. 100 nanometers. That's 10,000 times thinner than a human hair, smaller than the wavelength of visible light. These crystals form around meteor dust, tiny particles left behind by comets and asteroids burning up in the atmosphere. When water vapor, rare at these altitudes, encounters these dust particles at temperatures of minus 140 degrees Celsius, it freezes onto them, creating clouds so high and so thin that they're invisible during the day. But during deep twilight, specifically during astronomical twilight, something remarkable happens. The sun, far below the horizon from the perspective of someone on the ground, still illuminates these highest clouds. They glow electric blue against a darkening sky, showing intricate wave patterns and structures, visible for perhaps 30 minutes before the sun drops so low that even they fall into Earth's shadow. You can only see noctilucent clouds during summer, only between 50 and 70 degrees latitude, only during the deepest part of twilight, and only if you're looking at the right part of the sky at the right moment. This is perhaps the most exclusive show in Twilight's repertoire, a phenomenon that requires specific season, specific latitude, specific time, and specific sky conditions all to align. When they do, what you see is unlike anything else in nature. Clouds that shouldn't exist, ice at temperatures cold enough to freeze carbon dioxide, floating where air is thinner than in laboratory vacuum chambers, lit by a sun that set an hour ago from the viewer's perspective. They ripple and flow, showing atmospheric waves and dynamics that occur at the boundary between atmosphere and space. Scientists study noctilucent clouds partly because they're beautiful and partly because they're increasing. Observations suggest they're becoming more frequent and more visible at lower latitudes than they once were. The cause appears to be rising levels of water vapor in the upper atmosphere, a consequence of climate change and increasing methane, which breaks down into water at high altitudes. These ghostly clouds may be early indicators of how we're changing our atmosphere in ways that reach even to the edge of space. But whether you're watching the green flash or the belt of Venus, crepuscular rays or noctilucent clouds, you're witnessing the same fundamental phenomenon: light interacting with matter. Photons colliding with molecules and particles, bending around temperature gradients, scattering off ice crystals, revealing the structure and composition of our atmosphere in visible, tangible ways. Twilight doesn't just provide light, it provides illumination in the deeper sense. It lights up the invisible. It makes visible the layers and gradients and particles that exist always, but that we can't normally see. The green flash reveals atmospheric stratification. The belt of Venus reveals planetary geometry. Crepuscular rays reveal three-dimensional structure in the air. Noctilucent clouds reveal dynamics at the edge of space. Each phenomenon is a window, a brief opportunity to see what's always there but normally hidden, and each one requires specific conditions, specific angles, specific atmospheric properties, specific times. They're not random, they're not accidents. They're natural consequences of how light behaves when passing through a stratified, particle-laden, temperature-variant atmosphere surrounding a rotating planet. This is why twilight has captivated observers for millennia, not just because it's beautiful, though beauty matters, but because it reveals, it teaches, it shows us our world's workings through direct observation. You don't need a laboratory to see atmospheric layers. Just watch the green flash. You don't need instruments to measure planetary shadow, just observe the belt of Venus. You don't need satellite data to understand atmospheric structure, just study crepuscular rays. Everything you need to begin understanding atmospheric physics is available twice daily, free of charge, visible to anyone who bothers to look up during those transition minutes between day and night. Twilight is a laboratory that comes to you, performing experiments in real time, displaying results across the entire dome of the sky. And tomorrow, we'll explore how life itself has learned to read these signals, how plants and animals and even humans have evolved exquisite sensitivity to twilight's changing light, using it to time activities, navigate across continents, and synchronize biological processes that govern everything from flowering to migration to sleep. But tonight, if the sky is clear, watch for these phenomena. Look for the green flash as the sun sets. You'll need a clear horizon and keen eyes. Turn around and find the belt of Venus rising in the east. If clouds are present, watch for crepuscular rays. And if you're in the right place at the right season, scan the northern or southern sky during deep twilight for the electric blue glow of clouds that shouldn't exist. Because these aren't distant astronomical phenomena requiring telescopes, they're not microscopic events requiring special equipment. They're happening in your sky, over your head, at a scale you can see with naked eyes. Nature's greatest light show, performed daily, awaiting only your attention to reveal wonders that most people miss despite looking at the same sky throughout their entire lives. The universe doesn't hide its beauty, it displays it openly. You need only learn where to look, and when, and what you're seeing when you find it. Twilight teaches this lesson better than perhaps any other natural phenomenon, that knowledge transforms observation into understanding, and understanding transforms the familiar into the extraordinary. 400 million years ago, plants took their first tentative steps onto land. They left behind the ocean, where light filtered down through water in predictable patterns, and encountered a new challenge: the unfiltered intensity of the sun. Too much light damages cellular machinery. Too little, and photosynthesis fails. The solution required precision timing, knowing when to open stomata, when to begin growth processes, when to prepare for night. Those ancient colonizers evolved something remarkable: circadian rhythms tied specifically to twilight's changing light. Deep within their cells, photoreceptor proteins developed that detect exactly 8 lux. Not 10 lux, not 5 lux, 8 lux, a threshold that sits precisely within twilight's range, marking the transition between day and night operations. Think about what this means. 400 million years ago, plants were already measuring light with precision that matches our modern instruments. They were already using twilight as a signal, a trigger, a synchronization point for biological processes that continue to this very day in their descendants. Walk through a garden at dusk, and you'll see this ancient inheritance in action. Evening primrose stands waiting, its petals furled tight against the day's heat. Then, as twilight reaches a specific threshold as light drops, below 100 lux something extraordinary happens. The petals unfurl, not slowly over hours, but in exactly 4 minutes from start to finish. 4 minutes. You could sit and watch the entire process, the flower opening like a time-lapse film playing at normal speed. And as those petals spread wide, specialized cells release linalool molecules, a fragrant compound that wafts on twilight breezes, traveling up to 2 kilometers from the flower. Those molecules are a signal, an advertisement, a beacon specifically designed for sphinx moths, insects that fly during twilight and whose tongues extend 30 centimeters to reach nectar hidden deep within the primrose's throat. The timing is exquisite. Flowers open precisely when their pollinators are active. Chemical signals release precisely when air currents are most likely to carry them. It's a coordination perfected across millions of years, synchronized to twilight's arrival. But plants aren't the only organisms that keep this ancient appointment. Honeybees, those industrious collectors of nectar and pollen, perform their final orientation flights at civil twilight's end. Watch a hive as the sun sets. Workers that have spent the day foraging return, their bodies laden with provisions. But before entering the hive, they perform a curious behavior. They fly in loops and spirals around the entrance, as if memorizing its location. They are memorizing it, but not using visual landmarks the way you might. Instead, they're reading polarized light patterns invisible to human eyes. When sunlight scatters through the atmosphere, it becomes partially polarized. The electromagnetic waves oscillate in preferred directions. The pattern shifts throughout the day, but it's particularly distinct during twilight, when light comes from specific angles and passes through maximum atmosphere. Bees have evolved photoreceptors that detect this polarization, essentially seeing a grid or map in the sky that remains constant even when the sun itself isn't visible. They use this grid to navigate, to maintain direction, to find their way home. And twilight, with its enhanced polarization patterns, provides the optimal time for learning this map. Young bees perform orientation flights during twilight specifically because that's when the navigation signals are clearest. As bees return to their hives, another performer takes the stage. Fireflies begin their displays when ambient light falls to precisely 0.1 lux. Not at sunset, not in full darkness, but at that specific threshold within nautical twilight, when light has faded just enough for their bioluminescent signals to stand out against the background. The chemistry is remarkable. Inside specialized cells called photocytes, fireflies combine a molecule called luciferin with oxygen, catalyzed by an enzyme called luciferase. The reaction produces light at 96% efficiency, meaning 96% of the energy goes into light production rather than waste heat. Compare this to LED bulbs, our most efficient artificial lights, which achieve only 20% efficiency. Incandescent bulbs manage a mere 5%. Fireflies, through evolution, have solved a problem that still challenges our best engineers: how to produce light without producing excessive heat. And they've done it at scales we can barely replicate, in cells smaller than the width of a hair, using organic chemistry that operates at body temperature. But they didn't evolve this remarkable ability for our entertainment. The flashes are communication. Males flash specific patterns while flying species-specific codes that identify them to potential mates. Females, perched in grass or on leaves, watch for the correct pattern. When they see it, they flash back in response, and the male flies toward the signal. The entire system works only because they've synchronized to twilight. Flash too early, in bright light, and the signals vanish in glare. Flash too late, in full darkness, and the visual context disappears. Females can't judge the male's flying ability, size, or health. But at 0.1 lux, during nautical twilight, both the flashes and the environment remain visible. The lighting is, quite literally, perfect for their purposes. While fireflies flash in meadows and gardens, something even more extraordinary is happening in the ocean. At twilight's arrival, 540 billion tons of plankton begin to rise from depths of 1,000 meters toward the surface. 540 billion tons. That's not a misprint. Nearly 500 billion tons of living organisms, performing the planet's greatest migration twice daily, synchronized to twilight's arrival. This is the deep scattering layer, named because it's dense enough to reflect sonar signals, creating a false bottom that appears on depth sounders. During daylight, these organisms' copepods, krill, small fish, jellyfish, remain in dark depths, where predators that hunt by sight can't find them. But at twilight, they rise to feed on phytoplankton that can survive only near the surface where sunlight penetrates. They don't rise randomly. They time their ascent to arrive at the surface precisely during twilight, when light levels are low enough to provide cover but high enough that they can still see to feed. Too early, and surface predators pick them off easily. Too late, and they miss the optimal feeding window. Evolution has tuned their timing to within minutes. Following the plankton come lanternfish, small, silvery fish that make up perhaps 65% of all deep-sea fish biomass. Their name comes from photophores, specialized organs that produce light along their bodies. During their twilight rise, these photophores glow at wavelengths that exactly match twilight's remaining light. This is counter-illumination, one of nature's most sophisticated camouflages. Predators below looking up would normally see the lanternfish, silhouetted against the brighter surface. But the photophores emit light downward at precisely the wavelength and intensity of the twilight filtering down from above. The fish becomes invisible not by turning dark, but by matching the background light so perfectly that it disappears. The precision required is extraordinary. Too bright, and the fish glows like a beacon. Too dim, and it appears as a dark shadow. But match the ambient twilight exactly, and detection becomes nearly impossible. Evolution has equipped these fish with light organs that automatically adjust output to match the changing illumination as they rise through the water column during twilight's progression. But perhaps the most profound response to twilight is one you carry with you constantly: melatonin production in your pineal gland. This tiny organ, about 8 millimeters long and shaped like a pine cone, sits deep in your brain. It has one primary function: regulating your sleep-wake cycle. And it does this by responding to twilight. When light drops below 10 lux, deep within civil, twilight-specialized cells in your retina begin sending signals to your pineal gland. These aren't the rods and cones that create vision. They're intrinsically photosensitive retinal ganglion cells, discovered only in the late 1990s, that detect overall light levels rather than forming images. These cells trigger melatonin production. This hormone doesn't cause sleep directly, that's a common misconception. Rather, it signals to your body that night is approaching, triggering a cascade of physiological changes. Core body temperature begins to drop, blood pressure decreases, alertness diminishes. You naturally begin feeling sleepy 30 to 45 minutes after sunset as melatonin levels rise. This rhythm is so fundamental that even people who are completely blind, who have no conscious light perception whatsoever, still maintain it. Those specialized retinal ganglion cells can function even when all other photoreceptors are damaged. They detect light, they signal twilight's arrival, and they maintain circadian rhythms that synchronize your biology to Earth's rotation. What's remarkable is that this system is ancient, not as ancient as plant photoreceptors, but ancient enough. Mammals evolved circadian regulation tied to twilight hundreds of millions of years ago. Your sleep-wake cycle isn't a learned behavior or a cultural construct. It's biology, written into your genes, responding to environmental cues that have existed as long as Earth has had an atmosphere. Disrupt this rhythm through artificial light, jet lag, shift work, and health suffers. Sleep quality deteriorates. Hormone production shifts. Even cellular repair mechanisms, which operate primarily during sleep, function less efficiently. We evolve to follow twilight's signal. When we ignore it, consequences follow. This is why camping, sleeping outdoors, exposed to natural light cycles so reliably improves sleep for most people. It's not just fresh air or exercise, it's circadian resynchronization. Away from artificial lights, your body can detect twilight accurately. Melatonin production begins at the proper time. Sleep comes naturally when it should. You wake with dawn rather than to an alarm. The system functions as evolution designed it. But the story doesn't end with individual organisms responding to twilight. Entire ecosystems shift at this transition. Diurnal animals, those active during day, retire to nests, burrows, and roosts. Nocturnal animals emerge. The soundscape changes as birdsong gives way to cricket chirps and frog calls. Predator and prey relationships flip as different hunters take over different territories. Stand in a forest at twilight and pay attention to the transition. It's not gradual. It's surprisingly abrupt. There's a moment often occurring within a 5-minute window when the shift happens. Bird calls that filled the air minutes ago suddenly cease. A brief silence follows, almost eerie in its completeness. Then the night singers begin. Crickets, katydids, tree frogs, owls. This isn't coincidence. It's competition management through temporal segregation. Diurnal and nocturnal species divide the same resources, food, space, nesting sites, by dividing time. And twilight is the boundary, the transition zone where one shift ends and another begins. The timing has to be precise, or the system breaks down. Species that miscalculate and become active too early or too late find themselves exposed to predators, and they're not adapted to handle or competing with species better equipped for current light conditions. Twilight acts as a reset button for ecosystems. Twice daily, the world reorganizes itself. New actors take the stage, new dynamics govern interactions. The forest or grassland or desert isn't the same place at twilight that it was at noon. It's fundamentally transformed, operating under different rules, hosting different communities, governed by different selective pressures. And at the center of this transformation is light. Not the presence or absence of light, but light at specific intensities, specific wavelengths, specific rates of change. Twilight provides a gradient that organisms use as a cue, a signal, a synchronization mechanism that coordinates activity across entire ecosystems. This is what 400 million years of evolution produces: exquisite sensitivity to subtle environmental signals. Plants that measure light to within a few lux, insects that detect polarization patterns invisible to most animals, fish that match their bioluminescence to ambient illumination with extraordinary precision, mammals whose sleep-wake cycles respond automatically to twilight's arrival. None of this is conscious. Plants don't decide when to open their flowers. Fireflies don't choose when to flash. Your pineal gland doesn't think about when to produce melatonin. These are automatic responses, evolved and refined across countless generations, tested against the ultimate criterion, survival and reproduction. Organisms that responded to twilight appropriately left more offspring. Those that didn't. Over millions of years, this simple algorithm respond well to twilight and reproduce, or respond poorly and fail shaped life into forms that treat twilight not as an incidental transition, but as a fundamental environmental parameter, as important as temperature or rainfall or seasonal change. When you watch evening primrose opening at dusk, you're witnessing an adaptation perfected over geological time. When you see fireflies beginning their displays, you're observing communication systems tuned to twilight-specific light levels. When you feel sleepy as the sun sets, you're experiencing biology that connects you to ancestors who lived and died by their ability to respond appropriately to the day-night transition. Twilight isn't peripheral to life. It's central. It's the signal that coordinates planetary-scale biological processes. It's the cue that tells organisms when to switch between different operational modes. It's the boundary that allows different species to share the same space by dividing time. And it all works because twilight is reliable. It arrives every day, at predictable times determined by latitude and season. Its intensity follows predictable patterns governed by atmospheric physics. Its duration varies in ways that organisms can track and anticipate. Evolution can work with reliable signals. Unreliable ones provide no basis for adaptation. But twilight is both reliable and rich with information. It doesn't just signal day ending. It signals exactly how far the sun has descended, what the current light level is, how fast light is changing, what wavelengths remain available. Each piece of information is useful for something. Each has been incorporated into biological systems. This is the beauty of evolution. Given time and reliable environmental patterns, life finds ways to use every available signal. Twilight represents one of the most reliable patterns on Earth. It's occurred every single day for billions of years. Life has had ample time to evolve responses to it, and those responses, accumulated across millions of species, create the spectacular coordination we see in ecosystems, shifting from day to night activity. Tomorrow, we'll explore how twilight changes as you move across Earth's surface, how those 12-minute equatorial twilights stretch to hours at high latitudes, how the midnight sun creates endless twilight during polar summer, how altitude and atmospheric conditions modify twilight in surprising ways. But tonight, step outside during twilight and pay attention to what's happening around you. Notice when birds stop singing. Watch for flowers opening. Listen for the first crickets. Feel your own alertness beginning to shift as melatonin production starts. You're not just observing twilight, you're participating in it. Your biology is responding to the same signals that govern evening primrose and fireflies and lanternfish. You're part of the system, synchronized to the same ancient rhythm that has coordinated life on this planet for hundreds of millions of years. The light is fading. Your pineal gland is responding. Melatonin is beginning to flow. And somewhere, flowers are opening. Bees are learning to navigate. Fireflies are beginning to flash. And 540 billion tons of plankton are rising toward the surface. All because the sun has dropped below the horizon, and light is bending around the curve of the world, creating this remarkable transition we call twilight. Stand on the equator in Quito, Ecuador, or Kampala, Uganda, or Pontianak, Indonesia, and watch the sun set. You'll witness something that people at higher latitudes find almost shocking. The sun doesn't leisurely descend, it drops, straight down, perpendicular to the stray horizon, at 15 degrees per hour. Twilight arrives and departs in exactly 12 minutes. 12 minutes from sunset to darkness, every single day of the year. This is geometry in action. At the equator, Earth's rotation carries you eastward at 1,670 kilometers per hour. The sun's apparent path is perpendicular to the horizon. It rises straight up at dawn and drops straight down at dusk. There's no shallow angle, no extended twilight. The transition is abrupt, almost violent in its suddenness. People who grow up near the equator experience a different relationship with twilight than those from higher latitudes. There's no long golden hour, no extended dusk to linger in. The day ends quickly, giving perhaps 15 minutes to complete outdoor tasks before darkness makes them difficult. This has shaped everything from architecture, why so many equatorial cultures developed enclosed courtyards and indoor gathering spaces, to social patterns, why evening meals often begin earlier than in temperate zones. But move north or south from the equator, and twilight begins to stretch. At 30 degrees latitude, Cairo, New Orleans, Shanghai civil twilight lasts about 24 minutes in spring and fall. The sun sets at an angle rather than dropping straight down. Light lingers longer, the transition softens. Continue to Paris at 49 degrees north, and the change becomes dramatic. During equinox, civil twilight lasts 34 minutes. But during June solstice, when the sun's path is most oblique to the horizon, civil twilight stretches to 52 minutes. Almost an hour of lingering light, creating those legendary Parisian summer evenings when dinner doesn't begin until 9 or 10, when sidewalk cafes remain full past 11, when the sky holds its blue until nearly midnight. This isn't culture-driving behavior, it's twilight's duration, enabling cultural practices. When evening light lasts nearly an hour, evening activities naturally expand to fill that time. Architecture adapts. Large windows to capture extended light, terraces and balconies for evening gatherings. Social patterns emerge around the long transition from day to night. But Paris is moderate. Push to Reykjavik at 64 degrees north, and during summer, twilight never ends. The sun approaches the horizon, but never descends far enough below it to end astronomical twilight. Instead, it skims along just beneath the horizon line, circling from sunset point to sunrise point, keeping the sky in perpetual twilight for weeks around summer solstice. This is the midnight sun, though that name is slightly misleading. The sun itself doesn't remain above the horizon at this latitude. What remains is twilight. Perpetual golden hour, 24 hours per day of light that's never quite daylight, never quite darkness. The sky cycles through colors gold to pink to deep blue to pink to gold again, but true darkness never arrives. The biological consequences are profound. Reindeer in Iceland graze continuously during summer twilight, unable to distinguish day from night, feeding for 19 hours straight. Arctic terns fly continuously, their internal clocks overwhelmed by the endless light. Even humans find sleep difficult. The normal melatonin response requires darkness, but darkness never comes. Visitors often experience insomnia. Locals use blackout curtains religiously, and then winter arrives, and the situation reverses. The sun never rises. But this doesn't mean perpetual darkness. It means perpetual twilight of a different sort. For weeks around winter solstice, the sun circles below the horizon between 6 and 18 degrees down, creating continuous nautical and astronomical twilight. The sky glows deep blue at midday. Stars remain visible even during the brightest hours. It's neither day nor night, but an extended transition that lasts months. Travel even farther north to Svalbard at 78 degrees, and the midnight sun lasts 4 months. The sun spirals upward in spring, circles the sky continuously all summer without setting once, then spirals downward in fall. Twilight, in the sense of the sun being near but below the horizon, effectively disappears during this period. It's replaced by constant daylight, albeit daylight that varies in intensity as the sun reaches higher or lower points in its circling path. But at McMurdo Station in Antarctica, 77 degrees south, researchers experience something even stranger. Between February and May, as the sun spirals downward toward winter darkness, it spends months circling just below the horizon, never rising, but never descending into full night either. 4 months of continuous twilight. 4 months when the sun circles between 6 and 18 degrees down, painting ice crystals in colors that shift from amber through magenta to deep violet as the sun's angle changes hour by hour. Imagine living in this environment. No sunrise, no sunset, no day-night cycle in any conventional sense. Just a slow progression as the sun spirals deeper below the horizon, over weeks, the twilight gradually dimming but never vanishing, until finally, in May, the sun descends past 18 degrees and true polar night begins. The psychological effects on research station personnel are well documented. Sleep cycles drift without the sharp day-night transitions that normally anchor them. Mood changes are common, not quite seasonal affective disorder, because there's still light, but a more subtle malaise that comes from living in perpetual transition, never fully experiencing either day or night for months on end. But latitude isn't the only factor that modifies twilight. Altitude matters too. In Death Valley, the lowest point in North America at 86 meters below sea level, twilight appears 16 minutes earlier than in the mountains just 50 kilometers away at 3,000 meters elevation. 2 minutes earlier. The cause is atmospheric bending. Light travels through air, and air density decreases with altitude. In Death Valley, you're looking through very dense hot air near sea level. This dense air bends light more strongly, allowing twilight to begin while the sun is still slightly higher above the horizon from a geometric perspective. In the mountains, thinner air bends light less. Twilight starts later because light must wait until the sun descends to a lower angle before atmospheric bending can lift it back to the observer. Pilots call this false twilight, and it's caused navigation errors. A pilot descending from high altitude sees twilight beginning later than ground observers do. If they're timing their approach by twilight's arrival, they might misjudge their altitude, thinking they're higher than they actually are because twilight hasn't arrived yet from their perspective, even though ground observers can already see it. Temperature inversions create similar effects. When warm air sits atop cold air, common in valleys on calm nights, the boundary between layers acts as a lens, bending light paths. Twilight can appear earlier or later depending on inversion strength and structure. In extreme cases, inversions create superior mirages, where the sun appears to set, then briefly reappear above the horizon, then set again. The same sun setting twice, because atmospheric layers bend its light in complex ways. Over water, twilight behaves differently than over land. Ocean twilight lasts about 8 minutes longer than land twilight at the same latitude. The reason is thermal. Water retains heat better than land, creating temperature inversions above the surface. These inversions bend light further around Earth's curve, extending the period when the sun's light can reach an observer even after geometric sunset. This is why sailors see the green flash twice as often as landlubbers. It's not just that ocean horizons are clearer, though that helps. It's that ocean inversions create stronger atmospheric lensing, which both extends twilight duration and enhances the prismatic separation of colors that creates the green flash. The same physics that makes ocean twilight last longer makes color separation at sunset more pronounced. At extreme northern and southern latitudes, these effects combine in remarkable ways. Polar seas during summer experience twilight that lasts not minutes or hours but days. The sun skims along the horizon for 48 hours or more. creating extended twilight periods punctuated by brief periods when the sun just barely rises above or sinks just barely below the horizon line. Water's heat retention extends these twilights even further, creating transitions measured in days rather than minutes. Mountains introduce another variable, line of sight. In valleys, surrounding peaks block the sun earlier than it actually sets from a geometric perspective. This creates valley twilight that begins early and lasts longer, because while the valley floor is in shadow, the sun remains above the horizon, illuminating the atmosphere above. Light scatters down from this illuminated air, creating twilight that continues long after direct sunlight has left the valley floor. Alpine climbers experience this regularly. At high altitude, they watch the sun set over distant peaks. But people in valleys below entered twilight 15 or 20 minutes earlier, when those same peaks blocked their direct view of the sun. The result is a temporal gradient. Twilight begins at different times, at different elevations and different positions in complex terrain, even at the same latitude and longitude. Desert twilight is distinctive for other reasons. Extremely dry air contains fewer water droplets to scatter light. This creates twilight that's shorter and less colourful than in humid regions. The sky might transition from blue directly to deep purple or black, skipping the orange and pink phases that characterize twilight in moister climates. Colours are purer but less varied. The transition is faster but less dramatic. Conversely, tropical rainforests experience some of Earth's most spectacular twilights. High humidity means abundant water droplets for scattering. Frequent afternoon convection creates dramatic cloud structures. The combination produces twilights rich in colour, long in duration, and highly variable from day to day. No two tropical twilights look alike because atmospheric conditions change so rapidly in these regions. Urban areas create their own twilight phenomenon, sky glow. Light pollution from cities brightens the night sky by scattering off atmospheric particles. This artificial twilight extends genuine twilight, creating a gradient where civil twilight blends imperceptibly into artificial twilight that persists all night. Within 100 kilometers of major urban centers, city lights brighten twilight by 300%. Astronomical twilight, the threshold where faint stars become visible, effectively ceases to exist. 2.8 billion people now live in areas where they never experience true astronomical twilight. The sky never gets dark enough for the faintest stars to appear. The Milky Way remains invisible. Zodiacal light is undetectable. They experience day and dim day, but not day and night in the way humans experienced it for all of evolutionary history prior to the last century. This has consequences. Circadian rhythms depend on detecting twilight's transition from 10 lux down to near zero. If artificial light keeps ambient levels above 10 lux throughout the night, melatonin production is suppressed. Sleep quality suffers. Health impacts accumulate. We've effectively extended civil twilight indefinitely in urban areas, creating an environment that our biology isn't adapted to handle. But in dark sky preserves areas specifically protected from light pollution, you can still experience twilight as humans have for millennia. The progression from civil to nautical to astronomical twilight happens in its natural rhythm. The sky darkens from blue through purple to black. Stars appear gradually, from brightest to faintest. The Milky Way emerges like fog made of light. This is the twilight that shaped our evolution, that governed our ancestors' activities, that our biology expects. Stand in such a place and watch twilight progress from start to finish. Notice how long it takes at your latitude. Feel how the air temperature drops as light fades. Watch how the wind often calms during twilight, a meteorological phenomenon caused by decreasing surface heating as the sun descends. Listen to how sounds carry differently as air temperature gradients shift. Twilight isn't just a visual phenomenon, it's a transformation of the entire environment. Temperature gradients change, air density shifts, sound propagation alters, wind patterns modify, animals respond, plants adjust. And these changes happen on a schedule determined by latitude, season, altitude, and local atmospheric conditions. This is why twilight has captivated observers across cultures. It's not the same everywhere. It's not even the same at the same location across seasons. It's infinitely variable within a consistent framework, always following the same physics, but expressing those physics differently depending on where you stand on Earth's surface and when you're observing. Tomorrow, we'll explore how humans have worked to capture and measure twilight from early photography that finally could record what painters had tried for centuries to depict, to modern satellites that measure twilight from space, to telescopes that use twilight's specific spectrum to calibrate their instruments. The story of twilight is also the story of observation and measurement, of human efforts to quantify and understand this daily phenomenon that's always been visible but only recently fully explained. But tonight, wherever you are, pay attention to how long your twilight lasts. If you're near the equator, mark how quickly it passes. If you're at higher latitudes, notice how it lingers. If you're in a valley, observe when twilight begins compared to higher terrain. If you're near water, see whether twilight persists longer than it would over land. Every observation adds to your understanding of how this phenomenon varies across Earth's diverse surface. Because twilight is local and global simultaneously, the same physics operates everywhere, but the results vary dramatically depending on where you stand. Understanding your twilight, its duration, its color, its progression connects you to your specific place on this planet, to the geometry of Earth's rotation relative to the Sun, to atmospheric conditions unique to your location and season. This is knowledge that comes only through observation. No book or lecture can substitute for actually watching twilight at your latitude, in your season, from your particular vantage point. The general principles are universal. The specific expression is unique to you. And that combination, universal physics expressing itself in location-specific ways, is part of what makes twilight endlessly fascinating to observe. In 1761, Mikhail Lomonosov stood with his telescope pointed at the sun. This was not casual observation. It was one of the rarest celestial events visible from Earth. Venus was about to transit the sun's face, passing directly between Earth and our star, appearing as a small black dot crawling across brilliant white. Astronomers around the world had positioned themselves to observe this transit. The measurements they took would help calculate the distance from Earth to the Sun, one of the most important astronomical measurements possible. But Lomonosov noticed something no one else did. As Venus touched the Sun's edge at the start of transit, he saw a glowing arc around the dark disk, a ring of light, where there should have been none. He understood immediately what he was seeing. Venus had an atmosphere. The ring was twilight, Venusian twilight, as sunlight bent through atmospheric layers around the planet's edge. This was the first proof that other worlds had air. Before spacecraft, before spectroscopy, before any modern astronomical technique, twilight revealed that Earth wasn't unique in possessing an atmosphere. Consider what this means. Twilight, the same phenomenon you can watch from your backyard, provided evidence for atmospheres on other planets. The physics are universal. Light bends through gas. If a planet has sufficient atmosphere, it will show twilight when backlit by the sun. Lomonosov saw this with an early telescope, from a single observation, because he understood what twilight was and what it revealed. This marked the beginning of humanity's systematic effort to capture and measure twilight. Before this, twilight existed only as direct experience. You watched it, you painted it if you were an artist, you timed your activities to it, but you couldn't preserve it. You couldn't analyze it later. You couldn't compare twilights across different locations and times in any rigorous way. Artists tried. Turner painted sunsets that captured something of twilight's color and drama, Japanese printmakers like Hiroshige created stunning twilight scenes. But painting is interpretation. It's the artist's perception filtered through their technical skills and aesthetic choices. Two artists watching the same twilight would paint it differently. And crucially, paintings couldn't answer quantitative questions. What was the exact color? How bright was it? How did it change minute by minute? Photography changed everything. The first permanent photograph, taken by Nicephore Niepce in 1826, required 8 hours of exposure in direct sunlight. It couldn't capture anything as brief or dim as twilight. But technology advanced. By the 1880s, exposure times had dropped to fractions of a second. Photographers could now capture moments rather than requiring their subjects to remain motionless for minutes. But there was a problem. Photography was black and white. You could capture twilight's brightness progression, its cloud structures, its changing contrast, but not its colors, the oranges and purples and deep blues that define twilight's visual experience. The invention that captured twilight's duration missed its most striking quality. Then, in 1907, the Lumiere brothers introduced autochrome, the first practical color photography process. For the first time in human history, twilight's colors could be preserved, not interpreted through paint, but directly captured through chemistry. Photographers rushed to document twilights, creating archives of images that finally allowed quantitative comparison. What they discovered was surprising. Twilight colors that artists had been painting for centuries, those deep purples and intense oranges, were real. Artists hadn't been exaggerating. If anything, they had been understating the drama. Twilight genuinely produces colors more saturated than midday light, more varied than any other natural lighting condition, changing so rapidly that even multiple photographs taken minutes apart show dramatically different conditions. But color photography revealed something else. Twilight's dynamic range, the ratio between brightest and darkest parts of the scene, is extreme. At civil twilight's beginning, clouds near the horizon might receive 30,000 lux of reflected sunlight, while shadows on the ground sit in near darkness at 2 lux. That's a range of 15,000 to 1, or about 14 stops in photography terminology. Human eyes can see about 10 stops of dynamic range. We evolved to function in this range, to extract information from scenes where bright and dark don't differ by more than about 1,000 to 1. But twilight exceeds this. There are parts of a twilight scene too bright for comfortable viewing, and parts too dark to see clearly, existing simultaneously. Early photographers had to choose: expose for the bright sky and lose all ground detail, or expose for the ground and blow out the sky to featureless white. There was no way to capture both. This frustrated generations of photographers who could see the full scene with their eyes but couldn't record it on film. The solution came through graduated neutral density filters, pieces of glass that are dark on one half and clear on the other, with a gradual transition between. Hold one in front of the lens, with the dark half over the sky, and you can reduce sky brightness without affecting the ground. This allows capturing closer to what the eye sees, though still not perfectly, because the eye isn't really seeing 14 stops simultaneously. It's rapidly scanning between bright and dark areas, adjusting pupil size and sensitivity, creating the impression of seeing the full range when actually it's sampling and integrating over time. Modern digital cameras do something similar. They can capture multiple exposures rapidly, one for bright areas, one for shadows, one for midtones, then combine them into a single high dynamic range image that shows detail throughout the twilight scene. But this is computational photography, not direct capture. The camera is doing what your eye does, sampling different brightness ranges and integrating them into a coherent image. Still, even HDR photography can't fully capture twilight. The colors aren't quite right. Sensors don't respond to wavelengths the same way your eye does. The temporal progression is lost. A photograph freezes one moment, when twilight is fundamentally about change. And the emotional impact differs. Looking at a photograph of twilight, no matter how technically excellent, isn't the same as experiencing twilight's progression in real time. This is why filmmakers, particularly in recent decades, have become obsessed with capturing magic hour, the period during civil twilight when light is soft and warm and everything looks cinematic. Entire productions schedule around it, racing to capture crucial shots during the 20 to 30 minutes when conditions are optimal. Some films have been known to shoot the same scene over multiple days, capturing different moments of the same twilight to edit together into a continuous sequence. But while photographers and filmmakers work to capture twilight visually, scientists developed ways to measure it quantitatively. Radiometers sensitive to 0.001 lux can detect light levels far below what human eyes can see. Spectrometers break twilight into component wavelengths, revealing not just colors, but the precise distribution of energy across the spectrum. These instruments, mounted on satellites, now measure twilight from space. They can track how twilight brightness changes with altitude, detecting the precise heights where different atmospheric layers scatter light. They can measure twilight globally, comparing polar and equatorial conditions simultaneously. They can track how volcanic eruptions or major dust storms modify twilight worldwide. One surprising discovery: city lights now brighten twilight by 300% within 100 kilometers of urban centers. This isn't just sky glow making the night sky brighter. It's actual modification of twilight itself, light from cities scattering off atmospheric particles during the twilight transition, adding artificial illumination that blends with natural twilight. For people living near cities, the twilight they experience is substantially brighter than the twilight humans experienced throughout evolutionary history. This has implications beyond aesthetics. Remember that many biological responses to twilight are triggered by specific light thresholds. If twilight never drops below certain levels because of light pollution, those responses don't trigger properly. Flowers that should open at a specific light level might open too early or not at all. Fireflies that flash at 0.1 lux might not flash if light never drops that low. The timing of ecosystem shifts gets disrupted. Satellite measurements have quantified this. 2.8 billion people now live in areas where astronomical twilight never occurs. The sky never gets dark enough for the faintest stars to appear. They experience civil twilight transitioning to artificial twilight that persists all night. True darkness is something they must travel to experience, if they experience it at all in their lifetimes. But satellites have revealed wonders too. In 2001, the Hubble Space Telescope detected twilight on an exoplanet, HD 209458b, a gas giant orbiting a sun-like star 150 light-years away, passed in front of its star from Earth's perspective. As it did, Hubble detected sodium atoms in the planet's atmosphere, glowing during the exoplanet's twilight. The same type of signature Lomonosov saw around Venus, but now detected across interstellar distances. This is extraordinary. We're detecting twilight on worlds so distant that their light takes 150 years to reach us. We're using twilight as a tool to study alien atmospheres, to determine composition and structure, to search for conditions that might support life. Twilight, once considered merely a transition between day and night, has become an astronomical instrument for characterizing planets around other stars. Modern ground-based telescopes use twilight for a different purpose: calibration. At the Mauna Kea Observatory in Hawaii, astronomers use twilight's specific spectrum to calibrate their instruments. Twilight provides a known light source with a predictable spectrum. By measuring how their instruments respond to twilight, astronomers can calibrate how those instruments will respond to faint starlight or distant galaxies. Specifically, they measure atmospheric water vapor by observing how twilight is absorbed at 935 nanometers, a wavelength where water molecules strongly absorb light. The amount of absorption tells them how much water vapor lies between the telescope and space. This is crucial information for correcting astronomical observations, because water vapor distorts starlight, smearing images and reducing clarity. So twilight serves double duty. It's both subject of study and tool for studying other things. We analyze twilight to understand atmospheric physics. We use twilight to calibrate instruments that observe the universe. The same phenomenon does both jobs because it's fundamentally about light interacting with atmosphere, which is what astronomical observation is fighting against when observing through Earth's air. Archaeologists have found evidence that humans have been carefully observing twilight for at least 5,000 years. Stonehenge's heel stone aligns precisely with the point on the horizon, where twilight begins during summer solstice. This isn't approximate, it's exact within the monument's construction tolerances. Someone who built Stonehenge understood twilight well enough to predict where, on the longest day of the year, the first light would appear. Why mark this moment? Perhaps religious significance associating the longest day with deities or seasonal cycles. Perhaps practical, using the alignment to track the calendar, ensuring agricultural activities happened at optimal times. Perhaps both. But the precision suggests careful observation over many years. Someone was watching twilight closely enough to recognize patterns, to determine that twilight begins at predictable locations on the horizon, to encode that knowledge in megalithic architecture. This theme repeats across cultures. Egyptian shadow clocks, Babylonian twilight tables, Islamic prayer times defined by twilight thresholds, Polynesian navigation techniques using twilight stars, Chinese records of unusual twilights associated with historical events. Humanity hasn't just experienced twilight, we've measured it, documented it, used it as a timing mechanism, incorporated it into cultural and religious practices. In the modern era, twilight affects everything from photography to aviation to military operations. Pilots need to know twilight duration when planning flights. It affects when they can see the horizon for VFR navigation, when they need instrument assistance, when landing becomes dangerous without lights. Military planners have entire tables for twilight duration at different latitudes and seasons, because twilight affects visibility for both observation and concealment. Photographers chase civil twilight obsessively, knowing they have perhaps 30 minutes to capture lighting that doesn't exist any other time. Astronomers wait impatiently for astronomical twilight to end so they can begin observations. Campers and hikers time their setup for arriving before nautical twilight ends, ensuring they can still see well enough to work, but taking advantage of twilight's softer light and cooler temperatures. And climate scientists track how twilight is changing. More water vapor in the upper atmosphere, a consequence of climate change, intensifies twilight colors but reduces visibility. Rising temperatures cause twilight mirages to appear 8 minutes earlier than a century ago. Changes in atmospheric particle composition from pollution affect twilight color distribution. Twilight serves as a sensitive indicator of atmospheric change, visible to anyone, but now also precisely measured by instruments that can detect shifts too subtle for human eyes. The quest to capture twilight continues. High-speed cameras can now record how twilight colors shift second by second. Spectral imaging can separate twilight into hundreds of wavelength bands, revealing how different parts of the spectrum change at different rates. Computer simulations can model twilight under different atmospheric conditions, predicting what future twilights might look like as climate continues changing. But here's what's remarkable. For all our instruments and satellites and sophisticated measurements, the most profound experience of twilight remains direct observation. Standing beneath the sky as colors shift, feeling temperature drop, watching stars appear, hearing the ecosystem transition from day to night activity. No instrument captures this, no photograph preserves it. No measurement quantifies the actual experience of being present during twilight's progression. This is why twilight continues to fascinate despite being so familiar. We can measure it precisely. We can photograph it beautifully. We can detect it on planets around other stars. But we can't fully capture or replicate the lived experience of watching day transform into night. Each twilight remains unique, unrepeatable, present only in the moment it occurs. And tomorrow will bring everything together, exploring how twilight continues its eternal dance across our planet, how it appears on other worlds, how climate change is modifying it, and what it means for the future. We'll look at twilight not just as phenomenon but as ongoing process, something that has occurred every day for billions of years and will continue long after we're gone. But tonight, if conditions allow, try capturing your own twilight. Use a camera if you have one. Take multiple exposures at different settings. See how hard it is to capture what you're seeing with your eyes. Notice what the camera captures that you didn't notice directly, and what you see that the camera misses. The attempt to capture twilight teaches you what twilight actually is, a dynamic, multi-dimensional phenomenon that resists reduction to any single image or measurement, because that's what humanity's quest to capture twilight has really taught us. Twilight is richer and more complex than any single representation can convey. Every method we've developed, painting, photography, spectroscopy, satellite measurement, reveals different aspects while missing others. The full phenomenon exists only in direct experience, in standing beneath the sky and watching it change. All our technology has enhanced our understanding, but it hasn't replaced the need to simply pay attention to what's happening above us. And that, perhaps, is twilight's most valuable lesson. Some things must be experienced directly to be truly known. Measurement and analysis enhance understanding, but they don't substitute for presence. You can study twilight for years through instruments and still be moved by actually watching it unfold in real time. The data informs, but the experience transforms. This is why astronomers, who understand twilight's physics better than anyone, still stop what they're doing to watch particularly spectacular sunsets. Why photographers who have captured thousands of twilights still feel compelled to capture one more. Why people who see twilight every day of their lives can still be captivated by an especially dramatic display. Familiarity doesn't breed contempt with twilight. If anything, deeper understanding increases appreciation. Learning why the sky turns orange doesn't diminish the beauty, it enhances it. Understanding atmospheric scattering makes the colors more remarkable, not less. Knowledge of the physics makes you appreciate how precisely conditions must align to create particularly stunning displays. And this knowledge is accessible. You don't need advanced degrees or expensive equipment to understand twilight. You need eyes, attention, and willingness to observe patterns over time. Ancient astronomers figured out fundamental principles using nothing but careful observation. You can too. Start simple. Notice when twilight begins at your location. Track how this changes throughout the year. Observe how duration varies with season. Pay attention to colors, how they progress, which appear first, which last longest. Note how clouds affect the display, how humidity influences color intensity, how clear air produces different results than hazy air. Do this consistently, and patterns emerge. You'll develop intuition for when twilight will be spectacular, based on afternoon cloud patterns. You'll recognize the specific humidity and clarity conditions that produce the most intense colors. You'll understand how your local geography, mountains, water bodies, urban development modifies twilight in ways unique to your location. This is knowledge that comes only through observation. No book can tell you exactly how twilight behaves where you live. General principles apply everywhere, but specific expression depends on local conditions. You become the expert on your twilight by watching it repeatedly, by noting patterns, by building a mental model of how atmospheric conditions translate into visual displays. And once you have that knowledge, Once you can predict when twilight will be remarkable and why, you've connected to a tradition that extends back millennia. Those Egyptian astronomers tracking twilight duration, Al-Biruni, calculating Earth's radius from a mountaintop, Polynesian navigators using twilight stars, Lomonosov detecting Venus's atmosphere. They were all doing the same thing, observing carefully, noting patterns, building understanding from direct experience. The tools have changed. We have cameras and satellites and spectrometers they couldn't imagine. But the fundamental process remains. Pay attention, note patterns, develop understanding. Twilight rewards this attention. The more you watch, the more you see. The more you understand, the more you appreciate. It's a phenomenon that reveals itself gradually to patient observers, offering endless depth to those willing to look closely. Tomorrow, in our final chapter, we'll explore Twilight's eternal dance, how it sweeps across Earth continuously, how it appears on other worlds, how it connects past and future, and what it means for our changing planet. We'll see Twilight not as isolated event but as ongoing process, part of planetary systems that have operated for billions of years. But tonight, think about what humanity's quest to capture Twilight has accomplished. We've photographed it, measured it, detected it on distant planets, encoded it in monuments, used it for navigation and timekeeping, studied it for climate signals. Yet it remains immediate and accessible, happening outside your window every evening, requiring no special equipment to observe, offering itself freely to anyone who bothers to look up. This combination, scientifically profound yet personally accessible, is rare. Most natural phenomena worth studying in depth require special circumstances to observe. Twilight requires only that you step outside and pay attention for 30 minutes. It's both everyday miracle and subject of cutting-edge astronomy. Both ancient human preoccupation and modern research focus, both simple beauty and complex physics. Understanding this doesn't diminish Twilight's wonder. It amplifies it. Knowing that the orange glow comes from light traveling through 40 atmospheres of air makes it more remarkable, not less. Recognizing that you're seeing the same phenomenon used to detect exoplanet atmospheres connects your experience to the forefront of astronomy. Realizing that the green flash you just saw lasts exactly 1.7 seconds because of precise atmospheric layering makes that flash more precious, not less magical. Science and wonder aren't opposites. They're partners. Knowledge enhances appreciation. Understanding deepens experience. The more you know about Twilight, the more you see when you watch it. And the more you watch it, the more you want to understand. It's a virtuous cycle where observation and analysis reinforce each other, each making the other more rewarding. This is humanity's relationship with Twilight distilled. We study it intensively, and we simply experience it, and both activities enrich each other. We don't choose between measurement and appreciation. We do both, and doing both reveals aspects neither would alone. Right now, at this very moment, Twilight is occurring somewhere on Earth. While you listen to these words, the sun is setting over some part of our planet's surface, bending light through atmosphere, painting sky colors that no human eye is witnessing because they're happening over empty ocean or uninhabited land. Twilight doesn't wait for observers. It happens continuously, ceaselessly, sweeping across Earth's face at 465 meters per second at the equator. 465 meters per second. That's how fast the twilight line moves as Earth rotates. Imagine standing at the equator and trying to keep pace with sunset. You'd need to travel at 1,670 kilometers per hour westward, matching Earth's rotation precisely. This is why equatorial twilight is so brief. You're rotating through it quickly, spending only 12 minutes in the transition zone as it races past. But here's what makes this profound. Twilight hasn't stopped since Earth developed an atmosphere. For 4.5 billion years, day has transitioned to night, and night to day through this twilight process. No interruption, no pause. An eternal wave circling the planet every 24 hours, regardless of whether anyone observes it, regardless of what happens on the surface below. Think about continuity on this scale. Empires have risen and fallen within a few thousand twilights. Human civilization spans perhaps 3 million twilights total. All of recorded history fits within 5,000 years, about 1.8 million twilights. But twilight itself predates everything human by such a margin that our entire existence barely registers as a momentary flicker in its endless progression. Before humans watched twilight, dinosaurs did, or at least experienced it, if they didn't contemplate it as we do. Before dinosaurs, the first land animals emerged during twilight. Before animals, plants learned to read its signals. Before life itself, twilight occurred exactly as it does now, governed by the same physics, following the same patterns, completely indifferent to whether living things existed to experience it. This is humbling in the best way. Twilight connects you to deep time. When you watch the sunset tonight, you're witnessing a process that has played out billions of times before and will play out billions of times after. You're part of a sequence that extends backward past all human history and forward past any conceivable human future. Twilight was here before us. It will persist after us. We're temporary observers of an eternal pattern. But twilight isn't unique to Earth. Look at Mars through a powerful telescope during its sunset, and you'd see something surprising. Blue twilight. Not orange-red like Earth's, but blue. The reason is dust specifically. Iron oxide dust that covers Mars's surface and fills its thin atmosphere. This dust scatters light opposite to how Earth's air does. Blue light scatters forward more efficiently than red, so the sun appears blue during Martian sunset. The sky around it glows blue. It's twilight, but inverted from what we experience. Martian twilight is brief, lasting perhaps 2 minutes through air at only 1% of Earth's atmospheric pressure. There's so little atmosphere to scatter light that the transition from day to night happens almost as abruptly as on airless Mercury, where the sun simply vanishes the instant it drops below the horizon, and darkness arrives instantly, like flipping a switch. No twilight at all on Mercury, no transition. Just binary states, day or night, light or dark, nothing between. Venus represents the opposite extreme. Its thick atmosphere rotates independently of the solid planet below, creating winds that circle Venus in just 4 Earth days, even though the planet itself rotates once every 243 days. When the sun finally does set on Venus, an event that happens only once every 116 Earth days, because Venus rotates so slowly, and backward twilight continues for the equivalent of nearly 4 Earth months. Imagine experiencing twilight that lasts 16 weeks. The sun sets, the sky begins its transition, and continues transitioning for 4 months before darkness finally, eventually arrives. This is twilight stretched to absurd extremes. Twilight as permanent state rather than brief transition. Venusian twilight isn't a moment you witness, it's a season you endure. Jupiter's moons experience twilight too, but uniquely. Io, the innermost large moon, has active volcanoes that continuously pump sulfur dioxide into its thin atmosphere. During Io's sunset, this sulfur scatters light in ways that create yellow-orange twilight unlike any other worlds. Europa, covered in ice and possessing an extremely tenuous oxygen atmosphere, has twilight so faint it's barely detectable. Yet it exists oxygen molecules scattering the last rays of sunlight before Jupiter's shadow engulfs the moon entirely. Even in the outer solar system, where the sun appears merely as the brightest star rather than a disk, twilight persists. Saturn's moon Titan has atmosphere thicker than Earth's 1.5 times surface pressure. Its sunset twilight lasts for hours, because Titan rotates slowly and has so much atmosphere to scatter light. But the light is dim, orange-tinted by organic haze, creating twilight that would seem more like deep dusk to human eyes, even at what Titan considers full daylight. Each world with atmosphere has twilight unique to its atmospheric composition, pressure, and rotation rate. Each one offers a different expression of the same fundamental physics, light bending through gas layers. But no other world we've yet discovered has twilight, quite like Earth's, that specific combination of duration, color, range, and biological significance that makes terrestrial twilight both beautiful and functionally important. This might change. As we discover exoplanets with Earth-like atmospheres, we'll eventually detect their twilights through spectroscopy. We'll measure how light from the parent star bends through alien air during planetary transits. We'll determine atmospheric composition from twilight signatures, searching for oxygen and water vapor and other biomarkers that might indicate life. Twilight will become a tool for finding habitable worlds, just as Lomonosov used it to discover Venus's atmosphere. But even closer to home, twilight is changing. Not in its fundamental physics. Light will always bend through atmosphere according to the same laws, but in its specific expression on Earth. Our planet's atmosphere is shifting in composition and behavior, and twilight reveals these shifts with particular clarity. Water vapor in the upper atmosphere has increased by 0.03% per decade over the past 50 years. This sounds trivial until you realize that water vapor is the most effective greenhouse gas and the most important factor in cloud formation. More water vapor means more intense twilight colors. Those deep oranges and purples become more saturated, but also more clouds that can block twilight entirely. At the same time, particulate pollution has decreased in some regions and increased in others. Fewer sulfur particles from reduced coal burning in North America and Europe means less intense twilight scattering in those regions. Sunsets are actually less red than they were in the 1970s. But increased dust from desertification in Africa and Asia means more dramatic twilights downwind of those regions. Twilight's appearance is shifting geographically as humanity's impact on atmosphere redistributes. Rising temperatures are creating stronger temperature inversions, layers, where warm air sits atop cold air, which increases atmospheric lensing. Twilight mirages, once relatively rare, now appear 8 minutes earlier on average than they did a century ago. The green flash, requiring specific atmospheric layering to occur, is becoming slightly more common in some locations and less common in others as thermal structure shifts. These changes are subtle. No single twilight shows them clearly. But average them over decades, compare measurements from different eras, and patterns emerge. Twilight is sensitive to atmospheric conditions in ways that make it an indicator of environmental change. Scientists now track twilight characteristics as a climate metric, one more signal in the complex data set of how our planet is transforming. Yet through all these changes, some natural, some human-caused twilight's fundamental structure persists. Civil twilight still occurs when the sun drops 6 degrees below the horizon. Nautical twilight still marks the transition where color vision fails. Astronomical twilight still defines the threshold where faint stars appear. The physics hasn't changed. The categories remain stable. Only the specific expression within those categories shifts with atmospheric conditions. This stability within variability is part of what makes twilight endlessly fascinating. The framework is constant. The details are infinitely variable. No two twilights are identical, yet all follow the same basic progression. It's like music. Every performance of a symphony is unique, yet all follow the same score. The constancy provides structure. The variation provides interest. Consider that future space colonies will need to recreate twilight. Humans evolved under Earth's day-night cycle, with its specific twilight transitions. Our circadian rhythms expect it. Our psychological well-being depends on it. So, rotating space, habitats at Earth-Moon Lagrange points or orbiting Mars, will will almost certainly include artificial twilight or gradual transitions from day to night rather than abrupt switches. Designers are already planning 30-minute twilight transitions for these habitats, carefully programming LED lighting systems to shift through the color, temperature, and brightness changes that characterize natural twilight. The goal isn't just aesthetic, it's biological necessity. Without proper twilight transitions, human inhabitants experience disrupted sleep, mood disorders, and reduced cognitive performance. We need twilight. Our bodies expect it. Future humans living in space will require artificial twilight, just as they'll require artificial gravity. This underscores how fundamental twilight is to human experience. We think of it as scenery, as aesthetic bonus, but it's actually functional necessity, a signal our biology depends on for proper functioning. Twilight isn't decoration. Its infrastructure is essential to human well-being as clean air or fresh water, just less obviously so because we've always had it, and rarely consider what life would be like without it. Back on Earth, as you drift towards sleep tonight, your body is responding to twilight signals that began when you saw the sun approach the horizon. Photons that left the sun 8 minutes ago struck your retina, triggering specialized cells that signaled your pineal gland to begin melatonin production. That melatonin is now affecting dozens of physiological processes, dropping your core temperature, reducing blood pressure, shifting hormone balances that prepare your body for sleep. But those photons traveled much farther than 8 minutes would suggest. They began their journey not at the sun's surface, but in its core, where nuclear fusion produces them. At the core's density, photons can't travel freely. They bounce between atoms, taking random paths. A single photon might travel only millimeters before being absorbed and re-emitted by an atom, then millimeters more in a random direction, then millimeters again. This random walk continues for 100,000 years. 100,000 years of bouncing atom to atom, slowly working outward from the core toward the surface. Finally, a photon reaches the sun's surface and escapes into space. Now it can travel freely, crossing 150 million kilometers in 8 minutes and 20 seconds, entering Earth's atmosphere, scattering through air molecules during twilight, and reaching your eye. The photon illuminating tonight's twilight is 100,000 years old. It began its journey when anatomically modern humans were just beginning to migrate out of Africa. It bounced through the sun while we were learning to control fire, developing language, creating the first art. It emerged from the sun's surface this morning, from our perspective, and completed its journey by painting the sky during this evening's twilight, before entering your eye and triggering a biological response that will help you sleep. This is the connection twilight provides between you and the sun, between present and deep past, between human biology and cosmic physics. Every twilight is ancient and immediate simultaneously. Ancient light, arriving now, eternal process, witnessed momentarily. And tomorrow, the cycle begins anew. The sun will rise, flooding Earth with light. Diurnal life will activate. Hours will pass in brightness. Then, as your part of Earth rotates away from the sun, twilight will return. The same progression, the same physics, the same biological responses. Different details, different clouds, different humidity, different precise colors, but the same fundamental pattern. This is twilight's eternal dance, reliable in structure, variable in expression, continuous in operation. It connects every moment to every other moment in an unbroken chain, extending backward billions of years and forward as long as Earth, retains atmosphere and orbits the sun. You're not watching an isolated event when you watch twilight. You're witnessing one iteration of a pattern that defines how light and atmosphere interact on a rotating planet. 50 billion more twilights have occurred on Earth since the first humans evolved. 50 billion opportunities to watch day transform into night through this precise sequence of atmospheric scattering. Most went unobserved. Many happened over empty oceans. Many occurred before anyone understood what they were seeing. But they all happened following the same physics, creating the same progression from bright to dark. You stand in that sequence tonight. One more observer in a chain extending back to the first humans who noticed patterns in Twilight's progression. One more moment when consciousness observes and appreciates this process that operates with or without observation. Your attention doesn't create Twilight, it just notices it. But noticing matters, understanding matters. Appreciation matters not to Twilight, which will continue regardless, but to you, because it connects you to something larger than yourself. When tomorrow's twilight arrives, remember what you're seeing. Light from nuclear fusion in the sun's core, released 100,000 years ago, completing an 8-minute journey to Earth, bending through atmosphere, because gas molecules scatter shorter wavelengths, more than longer ones, triggering biological responses in organisms that evolved to recognize this signal, creating colors and durations that vary with latitude and season, but always follow the same underlying physics. Remember that this same process is happening simultaneously elsewhere on Earth, that as your twilight ends, someone else's begins. Remember that it occurs on other worlds too, in forms both familiar and alien. Remember that it has continued uninterrupted for billions of years and will continue for billions more. And remember that despite all our understanding, despite satellites and spectrometers and computer models, twilight remains most profoundly experienced by simply stepping outside and watching it unfold. No instrument captures it completely. No analysis replaces direct observation. Knowledge enhances but doesn't substitute for presence. The eternal dance continues, tonight, tomorrow, every day, every world. Light bending through atmosphere, creating transitions between day and night, revealing the invisible, triggering life's rhythms, connecting past to present to future in an unbroken chain of photons and molecules and biological responses. Twilight isn't just what happens when the sun sets. It's what happens when light encounters matter, when physics becomes perception, when cosmic processes touch individual consciousness. It's the moment when you realize you're not separate from these patterns, but part of them, participating in systems that operated before you existed and will continue after you're gone, but which include you now, in this moment, as you watch day transform into night through the ancient miracle of light bending around the world.